we're always missing Mr. Yin Hao. I'm going to report him across the whole of the Pacific. All right, here he is. Here he is. All right, welcome to another class. I need to make a bunch of announcements so we don't forget them. The symposium for the class has been fixed. Hopefully that will work for you all as well. December 11 and 12. Okay? There is, and as a matter of fact, we may even have difficulties to find a room because it's an exam period and we need the rooms for the whole day basically, but that's the best I can do. Okay? 11th and 12th. And we hope to have both days basically completely filled. The attendance, of course, I wish I can say it's mandatory, but for me nothing is mandatory, but I would be disappointed if you come, you give a presentation, you leave, because the purpose of this workshop is to learn from your classmates and friends, okay? So plan to do nothing else. Nothing else. Don't eat, don't drink, just be there. All right. Some good news that I was told may not be good news for some. In other ways, some may complain. There will be no class after November 15th. Okay? November 15th is the week just before Thanksgiving. No, actually, is it? No. So the week of 15th is Thanksgiving, so no big deal, because anyways, there are no classes in principle. The week after that, there are classes, but I think study week. So we will have no classes. And I think the first week of December, I don't know if there are classes or not, there will be no classes. Okay? So effectively you have 3 weeks to prepare for your projects, but I do want to believe that you don't start those 3 weeks because you will never basically do much. Okay? So there will be no classes on November 15th, and what we need to do is not to miss any lectures. We're going to have to give no more than 2 extra lectures, and one of them is going to be this coming Friday. Okay? The other one we'll do it sometimes late in October, but remember this Friday there's going to be another lecture. Okay? Now, because on Friday we're supposed to have office hours, so we will have office hours 5 to 6 p.m. Our teaching assistant is volunteering to have office hours in his office, which is Fitzpatrick 155. For those in EE or CS that don't know, Ziz's office is 5 to 6 Fitzpatrick 155. This Friday only. Another reminder, this is the last week abstracts are due. If you send them to me by Friday and I don't like them, I am not going to be very happy. In other words, if you send something relevant and we don't even have one day to discuss it, that's not going to be good news. So please send me your abstracts today, tomorrow, Wednesday, so at least we have some room to iterate. Most of the abstracts come actually perfect for posting, so there's no discussion there. And remember, you need to send them in HTML format, not in Word, not in LaTeX. It has to be in HTML format. Okay? Any questions on these reminders? Of course, we're going to have office hours again today after the class, so you can come and see me for anything regarding either the homework or the projects. Okay. So we have, I think, maybe 15 lectures left, and obviously we are limited as to the type of topics we can cover, and even the sequence on the topics we cover. So I decided just to give you some breathing room, rather than continuing with something similar to regression, which most probably was going to be classification problems, to take a breather and discuss Monte Carlo methods. So spend maybe 2 weeks to give you a lot of interesting aspects of Monte Carlo methods. Even if these topics usually are not covered in machine learning courses. I don't really know why, but even in machine learning textbooks, you will see maybe a very elementary chapter of Monte Carlo methods, but for those who work on scientific applications, this is extremely important, okay? I mean, I used to have a very famous colleague in my former department who basically, he would not listen to anything else but Monte Carlo methods. He told me all the other methods for solving stochastic problems are baloney, all right? He just retired, I think, last year, so I'm sure he won't take the time to listen to my lectures. But, so Monte Carlo methods are extremely important. And if we have time today, we're going to start discussing a little bit about how do we generate samples from different distributions. And again, that's another topic you don't see much in machine learning textbooks. Of course, you will see books written on this subject from the statistics perspective. And I'm going to give you some reference to these books. So the key actually reference for most of the things that we're discussing is this book by Robert and Casella, Monte Carlo Statistical Methods. And for those who are going to work and do research in this area, I can tell you that there is whole series, like maybe 600 slides out of this book professionally done, and there are videos going with every chapter of the book. And there is way too much to learn if this is an area of interest to you. And of course you will get a sense that covering Monte Carlo methods is actually one semester course or maybe two. All right, of course, you're going to accuse me now with that I cover it in 2 lectures and very rapidly and I give you a headache, but that's better than zero. Right? Because if somebody comes and tells you go take another 2 courses, you're going to say forget about it. A book on Monte Carlo methods a little bit more relevant, especially to people in physics and biology and chemistry. This Monte Carlo strategies in scientific computing by Liu, and here and there I'm extracting some relevant topics that we're going to discuss today and the rest of the week and possibly early next week as well. Okay, and of course, if you search Monte Carlo methods, you will find many bigger universities than Notre Dame in size. They will have basically separate courses, and sometimes at the same semester, courses in biostatistics, in engineering, in operations research, in computer science at the same semester, so you can have a variety of ideas on the same topic. Because there's always something different to learn on these methods if the person who teaches them is a statistician, a computer scientist, a biologist, etc. Okay? All right. So let me put all of these things up and discuss why we need Monte Carlo methods. We already have introduced the concept. You have done sort of a little bit of a piece of the homework on this. So we computed the posterior distributions, all right? So in most occasions, these posterior distributions, of course, will be a complex computer code. I mean, most of the toy problems we did, because they were toy problems, this was some sort of a nice exponential family distribution. In the worst case, maybe some mixture of Gaussians or something like that. But generally speaking, when you do this calculation, this will be a computer code, and the only thing you can hope is to sample using that computer code. So of interest, of course, would be how do we get samples from this implicit posterior? And hopefully I will demonstrate today that for sampling, we don't really need to know the normalization factor, which is, as we know by now, it's a very complicated thing to compute. Okay? Now, of course, if you do need model selection, then you need to compute this integral. Okay, and this integral can be in very high dimensions, so even ideas of sparse quadrature methods may not be appropriate, and you may not have any choice but Monte Carlo. Okay, so 2 different problems. One to sample from the posterior, That is a subject of Monte Carlo methods. Another one is to compute integrals, and that's also the subject of Monte Carlo methods. Actually, possibly this week, I will give you enough sort of toy problems that I will convince you that every single task in numerical linear algebra can be done actually with sampling methods. Everything. Everything, like solving integral equations, solving eigenvalue problems, anything, of course, of every optimization problem, they all can be solved using Monte Carlo methods, and sometimes Monte Carlo methods are the only methods that we have available. All right, so sometimes maybe you don't care about the posterior, you care about point estimates, and we already have discussed the map estimate or the posterior variance, and you notice here the map estimate is a high dimensional integral, so Monte Carlo. The variance of the posterior theta is also requires integrals, so that's Monte Carlo again. So you cannot really escape from Monte Carlo methods. And I'm not going to elaborate today on this, maybe not at all in this class, but I can even claim that computing the map estimate can also be addressed with Monte Carlo methods. Can you just start thinking, so the map is the theta value that maximizes the posterior, so how is that possible that with samples you can actually compute the map estimate? So how is it possible that you can do optimization with sampling? I mean, obviously, when you take samples, right, the samples will be where the probability mass is maximum. So maybe you can, rather than sampling from this distribution, you can arrange it in such a way that samples basically come from the core of this distribution, and that will give you an estimate of theta map. And in that sense, every optimization problem can be addressed using Monte Carlo methods. This book by Liu that I mentioned on scientific computing and Monte Carlo methods actually emphasizes this in the context of applications in physics, chemistry, biology, so these are standard problems. By the way, don't do the mistake when you work in this area, let's say if you're a civil engineer, don't do the mistake and expect to find an answer to your problems in the civil engineering literature. All right, because I do think that's what a lot of students and professors think. That's the wrong way to go. I mean, it's very possible if it is something important that you are interested, maybe no civil engineer has done that, but the chances that somebody else in another community has done it is about 100%. All right? So you will be discovering something, say, wow, that's my PhD, when that has been a toy problem addressed back in the 50s. Okay, and I'm saying this because I already have witnessed that. Civil engineering was an example. The same is true with mechanical and every other discipline. Talking more about the use of Monte Carlo methods, to do predictions is also high dimensional integral. You remember that? So if I, let's say, train my model with data X, and I want to do predictions of some response, for new input to find the response Y, is basically nothing else but the integral of the likelihood, all right? The likelihood times the posterior, and this requires an integration in the parameter space, so that's a high dimensional integral, okay? And so how do we do that integral? Monte Carlo methods. There's really no other choice. Now, again, don't get misled by the fact that everything we did, this was coming in some nice form. This is only for classes. In reality, these integrals don't come in closed form. And, model selection, you already have seen how Bayes factors are computed in your homework with integration, with Monte Carlo integration. Okay. So let me do a toy problem, and maybe actually we already have discussed this in an early lecture, but it doesn't hurt anybody to see this again. So I want to compute pi, 3.14, whatever. All right, I want to compute this to any desired accuracy, and I want to do this with Monte Carlo integration. Okay, so this is sort of a standard toy problem. So we want to compute pi. Obviously, you affiliate pi with the area of a circle, right, or a sphere. So what I'm going to do is I'm going to start with a square of size 2 by 2, basically. The circle of radius 1 inside the square, all right? And I'm going to construct an experiment that, with Monte Carlo integration, will allow me to compute pi. Can you guess what that experiment may be? And actually, to conduct that experiment safely, I may have to go to the back of the room so you don't hear to me. So what that experiment may be? So again, I drew the square here, the circle, and we want to compute pi, which obviously comes in the area of the circle, and we're going to conduct a statistical experiment. So what that may be? So you're going to start throwing from where you are what? All right, so basically, I heard you saying, can we start taking samples inside the square, all right? Inside the circle and the points outside, all right? So let me repeat this for those listening to the tape. So basically the idea is, can we start taking samples in the square, the blue square, and see how many of those samples basically are inside the circle. Now, of course, when you say take samples, it requires a distribution. The question is, and what that distribution will be, right? And obviously, because we haven't discussed anything about sampling from different distributions, we hope this would be the common sense distribution, which is the uniform distribution. Okay? Now, the statement that, okay, we'll measure how many samples are going to be in the circle, how many outside in the square, requires a formal proof, right? This is not, we are doing things only that stand mathematically. So how do we actually prove this mathematically? The only thing we know with Monte Carlo, I remind you, is how to approximate the mean of a function, right, using the Central Limit Theorem effectively. And I will review those things for you. So what we need to do is, we need sort of to pose this problem as a problem of calculating integrals. And the question is what those integrals are going to be. You have to be careful to only tell you the very essential of what we need. Okay? So what integrals do you think we're going to compute? I'm going to jump a few slides. There is nothing in between really. This is, So I'm going to introduce, let's say we're throwing these darts, on the square, and they land, let's say, each of them in the location x and y. So what I'm going to do is I'm going to introduce an indicator function, all right? So for example, if A is the circle, all right? So if x and y is inside the circle, this indicator function for x and y will give me 1, otherwise 0, right? So can I pose the problem of computing pi, or how many samples are inside the circle versus outside, as the ratio of of two integrals, using this concept of indicator functions? Before I press the next equation, can you guess, using this indicator function, on how I can come up with something that looks basically the ratio of the area of the circle versus the area of the square? Yinghao, you should be talking loudly, because as I get older, I can barely hear you. Expectation of what? Be precise. I have a lot of expectations, but you know, if I'm not precise, I don't mean anything, right? And I'm referring beyond the class. Okay? So how about if I pose this probability of being inside the circle, all right? I'm ahead of myself. Let's say this is, you know, so I'm throwing a dart and I want to be sure, you know, that I count how many times it goes inside the circle and how many times outside. So the probability inside the circle, I am claiming that if S is my square, all right, that is the ratio of these two integrals. And I want you to convince yourself that this is right. You remember, if A is my circle, what is the integral on the top going to give me? Which we don't know, you know, we don't know anything, but it will give us the area of the circle, all right? Because this function, this indicator function, is only 1 inside the circle, 0 outside, okay? And this will give us the area of the square, which is, in this case, is 4. So if I rearrange and I put the 4th inside, I have the indicator function times 1/4 dx dy, and I have to compute that integral. And I remind you that the size of the square was 2 by 2, and we said because we don't really know anything else, we're going to sample uniformly, right? We're going to take samples uniformly inside the square. So if it is uniformly in x and y in that square, what is the probability of x and y? In each direction, it's square. So how much? 1/4. So what's 1/4? Is the probability of x and y, right? If you sample uniformly, right, in each direction, so 1/2 here times 1/2, you know, obviously I'm taking x and y to be independent. So this is the probability of x and y, a uniform probability, and this is a function, my indicator function, which is 1 inside the circle. So what is this integral under the uniform probability? It is the expectation of the indicator function. And how do we calculate the expectation using the Central Limit Theorem and everything else we discussed, right? The law of large numbers, etc., etc. How do you compute this? You sample uniformly the square, and then what do you take? We take 1/n times the summation of all of these indicator functions at each of the points. And for each point, the indicator function will be 1 only if it's inside the circle. So effectively, the ratio of the two areas, right, will be computed by the expectation of this indicator function, and that will give me an estimate of pi. Everybody says that? I remind you, right, and we will see the equations again from the Central Limit Theorem. The expectation, the way you compute this, as 1/n summation of this function computed at xi, yi for I 1 to n. So you take n samples in the square, and then you average the values of this indicator functions of those points divided by n. Okay? And again, this is equivalent to counting how many times these samples are inside the circle, because this function is only 1 if I'm inside the circle. So if you do that, so actually let me just remind you the general form for the, all right? So this comes with different versions of fundamental theorems in statistics, all right? So if you sample from some distribution, any distribution with mean mu and variance sigma squared, so the sample mean, all right, the sample mean approaches mu, the actual mean almost surely. This is a strong law of large numbers. The weak law is again that the sample mean goes to mu as n goes to infinity. The difference between really the weak and the strong law of large numbers is in the fundamentals of probability will not make any difference for us. And we also gave a more precise interpretation of what this means that as you take samples of size n, the probability that the sample mean will be away from the actual mean by a distance epsilon is practically zero as n goes to infinity for any epsilon. Okay? That's why you can surely say that xn, basically the sample mean x bar n, becomes equal to the actual mean of your distribution, and this is for any distribution, right? So no, it doesn't have to be Gaussian. Gamma can be any distribution. In our case, this was the uniform distribution, so it was quite an easy problem. And somewhere I also give you the central limit theorem that we have seen. So if you take the sample mean, follows a Gaussian distribution with mean, the actual mean of the distribution from where the data come, and variance sigma square over n. And the variance, of course, you don't know, right? I mean, even the mean mu you don't know, because that's why you take the sample mean, okay? You don't know this, but if you want to say something about your error in this approximation of mu with the sample mean, obviously you need to compute these error bars here, sigma over square root of n. So instead of sigma, what are you going to use? I mean, the only thing is you have samples, so you're going to use the sample variance, basically. Okay? There's really nothing else you can do, but this is very important, that the error bars is plus minus sigma over square root of n. Okay? Plus minus sigma over square root of n, and this will be also the error bars that we get when we do Monte Carlo approximations. All right. So, I want you to read the rest of the pi calculation, but basically, let me just, there's nothing there. It's basically that formula I gave you. I want to show you the final results, basically. What is my pi? All right? So, in the pi calculation, obviously you have to conduct the experiment, right? To find the indicator function, etc. But it comes out that the variance of your estimator is, I want to believe this is the variance for, let me see. Well, when I compute that integral there, right, you remember this is the integral over the circle, so you get 1/4 pi 1 square. So really this integral is pi over 4. So really we do Monte Carlo approximation of an integral that has an exact value pi over 4. Okay? So for this random variable, this is the variance that you get. Okay? Basically, the variance you can compute exactly in this type of problem. Okay? So it is pi over 4 minus pi over 4 squared. All right? So that integral comes to basically, central limit again. It converges to the exact pi over 4. All right? And the error that you commit is plus minus the variance of your estimator divided by square root of n. All right. And, I think we did this in maybe lecture 2 or 3. You can pose any sort of interesting questions, right? So the most interesting question is, how many samples do you need to take so that your approximation of pi is as accurate as you want? Is that possible to answer? I mean, we already know the error bars, right? Because the distribution follows a Gaussian form. So if somebody tells you, I want pi to be as accurate as 10 decimal digits, can you find how many samples you need to take for that accuracy? And the answer is you can do anything you want to, right? Because in our case, the estimator was an estimator of pi over 4, so the probability of being away from pi over 4 by any distance effectively, you can approximate it using the cumulative density function for the Gaussian distribution. So any questions that you want, so if you want this to be of a certain value, you can go back and compute how many samples you need to take for that to take place. And somehow I give you a table. Let me see if I can find it. So I give you a table where I do the following thing. I define the coefficient of variation as the standard deviation divided by the mean of my estimator. And in this problem, we know basically, we know this, right? It was in an earlier slide. I did not prove it, but it was straightforward to get that. The mean of the estimator, basically, this 1 over the square root of n, right, comes from this term here, okay? You remember the variance of the estimator is sigma square over n, all right? So sigma square is this term inside over n, because I have square root, it gives me that. And then the mean is pi over 4. So the coefficient of variation is this. So if you want a coefficient of variation to be 1%, then you need 2,739 samples. If you can live with 10%, then you can only take 28 samples. This, by the way, it's a very popular sort of measure for estimators, and I believe, I don't know if in our solution of Bayes factors we put this as a measure of an indicator of how well we converge with our Monte Carlo estimation, but basically that is something reasonable to do. So this is a definition, all right? The variance, the standard deviation of your estimator divided by the mean value, and then you decide what you need for COV, and that tells you how many samples you need to take. Just to give you some plots, by the way, these are, you can, there is, if you check on Wikipedia or in a good statistics book, you will find infinite set of inequalities that have to do with this Monte Carlo estimation, and all of this come basically by playing with the error function and the CDF of the Gaussian distribution. So here is for this area calculation for our estimator, different sort of inequalities that you can write down. They're all related to each other in principle. So if you're asking what's the probability that you are away from the exact value pi over 4 by epsilon, this comes to be less than 2 times e to the minus 2n epsilon squared. If you want this probability to be less than alpha, all right, so that's your confidence, and you don't want to be away with a higher probability, then the number of samples you need to take is given by this interesting term. And if you plug in the right values from this, if you want this probability to be less than 0.05, right, the way a frequentist may want to, then this epsilon here, it will be this square root of log 40 divided by 2n. This, inequalities are extremely important when you talk about convergence, okay? So when you play with Monte Carlo methods, you have to ask yourself, have I converged? All right, have I converged? Sometimes you have to take 1 million samples to converge, and this sort of inequalities may be very useful for your problem to tell you if you converge or not. So this is sort of a typical for our estimator, basically. And here we're plotting that ratio of the two areas that we had, minus pi over 4, which is the mean value. And so this will converge basically to 0, and you notice after 1,000 samples, it approaches 0, but it never gets really exactly 0. Okay? So it never gets exactly equal to 0. If you repeat this with different realizations, of course, every time you observe different things, but eventually all of them converge to zero as the number of samples increases. But you can argue here, even 1,000 samples is not enough. But you know what? If you want to calculate a pi, this is the way to do it. Actually, is there any other way? How do we compute pi from scratch? Do you know any other way in mathematics that you can compute pi? I'm just, my brain doesn't function right now. Any ideas? Series expansion, yeah. I suppose every series with sines and cosines and polynomials, plus, minus, they converge always to some powers of pi, okay? That would be too complicated for me, okay? Not to mention that you will have to look on what series is that, and here you don't really have to know anything. You conduct a simple experiment as what the value of pi is. All right. So let me generalize, which is the bottom line of what you need to know about Monte Carlo methods. Okay. So we started with the calculation of integrals like that. All right. So this is the expectation with respect to this distribution pi of theta, of f of theta, and f is some function of theta, okay, that we know. And you need sort of some very mild conditions for this to, basically you need to be sure that this expectation exists, okay? Otherwise, if you try to do it with Monte Carlo, you'll be wasting your time. You will never convert, so you need to be sure that this is finite. Actually, if you look, I believe on chapter 2 of the Bayesian core book that I gave you, he has several examples of computing the expectation of functions that don't converge. Okay? All right, so now, it doesn't mean that this function has to be continuous. Okay, because if it's discontinuous, when you integrate, you get zero contribution to the integral, but depends, of course, what is going on around the discontinuity. So anyways, we don't really need to worry right now. We suppose this thing exists, so we need to compute those integrals. So what you do is you take samples from the distribution pi of theta, and then with all versions of strong the last, Central Limit Theorem eventually, you get that the sample mean of f, it basically converges to the exact mean of the distribution of the function f of theta. Okay, so this is what we're interested. And if you want the error bars in this, you're going to have to calculate an approximation of the variance of this estimator. So here's the calculation. So let's do this. Basically, this is your estimator, and you're going to have to find the variance of that. All right? And I'm putting this equal to the exact variance divided by n. Would you agree with that? How do we get that? All these are IID samples, all right? So the variance of each of them is equal to the variance of that. So we're going to have what? What happened here? You have 1 over n, and then there is summation. How come I get 1 over n? When you have the variance of linear combination of these random variables, what do you get? You get 1 over n squared, and then there's going to be n times the variance of that, so you get 1 over n. Right? So, so the variance of the Monte Carlo estimator, this is extremely important, is the exact variance, right, divided by n. And if you want to see the form written, using the Central Limit Theorem, this is a Gaussian with the mean, the exact mean, and the variance is variance over square root of n. Okay. what is interesting that you need to notice, and I'm going to discuss this further, the dimensionality of theta doesn't come anywhere in this picture. So if you have 2 parameters, 25 parameters, a million parameters, I don't see this basically telling me anything about the dimensionality of theta. So basically, the variance, the error bars that you get is the, depends on n. So you get your classical error bars 1 over square root of n, but their dimensionality basically independent. Okay, so let me bring something else we have already seen. There's nothing new theoretically, just an interesting perspective. So let me put the whole thing up. You don't have to read anything. So let's say, we want to compute, we sample from a distribution pi of theta, right? That's what we had to compute before. We had to find the expectation of some function of theta, and we took n samples from this distribution pi of theta. So think each of the samples being a delta function, right? If I put them together, basically what we get is we get a mixture of delta functions that define sort of the sample representation of that distribution pi of theta. This is extremely important for Monte Carlo methods. So trying to get a sense of what this is, right? So we have the actual distribution, but the only thing we know about it is those samples theta phi. So if you want to represent this distribution, this is the sample version of the distribution, and the notation, of course, it's an approximation, so we put a hat. It's an approximation using n samples, and it is really a mixture of delta functions. Okay? And this, we will see that it will lead to ideas of people called particle approximations. Well, this is a particle approximation of the distribution of pi of theta, and what do we call particle? We call this samples theta phi. All right? And later on, we will see exciting things in the context of dynamical systems where we're going to allow these particles to evolve and move, right? Because the distribution changes, for example, let's say with time. So right now, this is the sample approximation of the distribution P of theta, okay? So since that equation is not written anywhere, can you tell me what is going to happen if I take the expectation of f of theta with respect to this distribution? So plug in, consider an integral of f of theta times this distribution, this sample approximation. Tell me, what did you get out of it? So you will get 1 over n, the summation of the function evaluations at the points theta I. Can you see that? Because when you multiply each of these delta functions with f of theta, you get f computed at points theta I. So really, the Monte Carlo approximation is the expectation of f of theta under which distribution? So before we write, we said, we have a distribution pi of theta. This is approximately the expectation of f of theta under pi of theta, and here's the approximation. Now, if you plug in this as pi of theta, you tell me you're getting exactly the Monte Carlo, the sample mean, basically, directly. So no approximations there. So the Monte Carlo estimator, it is really the expectation of f of theta with respect to what distribution? With respect to the sample distribution of pi of theta. I mean, if you use the original distribution, at the end of the day, really what you have done is substitute that actual distribution with this, because the only thing you know about pi of theta are the samples you collected. So in essence, the expectation of the function f of theta is nothing else but the expectation, the the Monte Carlo approximation of the expectation of f of theta is really the expectation of f of theta under the sample approximation of the distribution pi of theta. Okay? I'm showing here, for example, another similar calculation, but basically I want you to know that Monte Carlo estimations of all sorts of things implying approximating the distribution with its sample version, which is this mixture of delta functions. Okay? And something that I want you to keep in mind, in Monte Carlo approximations and in this sample approximation pi of theta, the weights are 1 over n. That will not be the case as we move on. All right? So right now the weights are 1 over n. This is Monte Carlo. But later on maybe we have some arbitrary weights that sum to 1, but they are not 1 over n. And that will need to wait maybe 2 lectures. Okay, so let me start giving you examples of these sample approximations of distributions. Okay, so this is a Gaussian, nice Gaussian, and those little delta functions is the sample approximation of the Gaussian. Now you may say, well, wait a second, this doesn't look a Gaussian. Well, it does, because you know what? This basically tells you not only where these tells you that you have these delta functions, but also that most of these delta functions are where the mass of the distribution is. Okay, so and of course, if you later on, and I think we will do this shortly, you will be able to take more samples of the Gaussian using only the sample approximation of the Gaussian. Okay, but just get used to the fact of representing distributions with samples and lots of delta functions. If you check physics books, the physicists were doing this type of calculations really back in the 30s and 40s, Actually, Monte Carlo methods were developed at the same time the nuclear bomb was developed, right, for that purpose. But really these calculations go back in physics, back in the 30s and possibly even earlier. All right, so here is this, we talk about the sample approximation of distributions and how you can use it to get approximations of expectations, which are integrals. So what I'm doing here is I give you a comparison between a deterministic calculation of an integral and a Monte Carlo calculation of an integral. And I want you to look at it. And so this is the function that I'm supposed to integrate. All right, so it's a function that has 2 modes. Okay, and I want you to tell me exactly what the 2 pictures basically show conceptually. So this is the deterministic, and these are really my samples that I will use to compute this with some quadrature rules. So when you do deterministic integration, what are these points? The way it is shown schematically here, right? There is no underlying theory that I'm trying to emphasize. But what's the idea when you try to calculate this numerically? Obviously, you have to evaluate the function in little pieces, little squares inside this domain. And those are samples that you take in x and y uniformly. Right? You don't have to do it uniformly. There are lots of quadrature rules and sparse grids that they try to mimic Monte Carlo methods, right? But, in a fundamental way, this is the starting point at least. Okay? And obviously you can see that the deterministic calculation of these integrals is wasting a lot of calculations and time because you are taking all the samples in this domain, in that domain, where the function is 0. So it's waste of your time. Now, in contrast to that, if you look at the Monte Carlo integrator, what does it do? What does it put the samples? Where the majority of the distribution is, of course, I don't show the actual distribution, right? But the idea is somehow we will be able to massage things that basically we sample where we need to sample an actual contribution comes from. Okay? And of course, you will find out that that requires sort of some imagination and some little tricks that you need to do to be sure that you sample from the right distribution doing this type of calculations. So this thing I was telling you with the sample approximation of pi of theta, and is given exactly here, right? So if you put those delta functions, right, in the expectation of f of theta, that integral, basically you get the sample mean of f. All right. So we mentioned that the convergence is basically independent of dimensionality. So let me just go to slide 43 in case that summarizes that as well. Okay, so the idea here is if you try to calculate an integral deterministically, so let's say, you know what, let's go back to this simple problem. Let's say there is no distribution, there is nothing there, and somebody tells you, compute for me this integral. How do you make that integral to be amenable to this Monte Carlo approximations? We need a distribution pi of x. So when there's no pi of x, what that distribution is going to be in that integral? I don't see pi of x there, so what do? Take it uniform, take it, 1, okay? And there is the expectation with respect to the uniform distribution. I mean, you don't need to go and massage things, it's obvious, it's 1, okay? So anyways, if you try to calculate this integral with deterministic methods, right, you're going to have to basically split this domain in every direction in little pieces. So, here these delta x's are 1 over n, and in one dimension only, and then go and calculate the function at each little squares in this subdivision, okay, and then sum all these contributions together, okay. So in d dimensions, basically you have to evaluate the functions n to the d times, right, n in the x direction, n in the y direction, n in the z, etc. And if you have 100 dimensions, you are ruined, basically. So if you want to achieve the same error that you get with Monte Carlo, this number of evaluations is going to be enormous. But in the Monte Carlo estimates, the Monte Carlo estimation, basically the convergence, it's maybe not as good as the one that you may achieve with some of these integration rules, but the number of points required is dimension independent, right? And you can get, again, an appreciation of the number of points that you need to integrate this function on the pi of x. In this case, deterministically versus a calculation that basically puts most of the samples for the probability masses. Okay. In the notes, basically, I put an example of the biggest factors that you guys did. So, all right, so let me, I'm going to change subject, still on Monte Carlo methods. And just take me the next 15 minutes. All right, so we need to calculate these integrals, and we need to calculate these expectations. And this is the algorithm, basically, all right, this is a summary of everything we have done up to now. There's really nothing beyond what is on this slide that you need. So if you have an integral like that, you will need to take samples from pi of x. This will be an approximation of this integral, of the expectation, will be your sample mean. And the variance is the variance of f of x divided by n, all right? I want you basically to remember every single thing that is given on this slide, but what I want to continue next is that all of these calculations basically will be useless unless I tell you how to take samples from a distribution pi of x. Okay? Now you may say, well, why do I need this? You know, if MATLAB and I don't know whatever, it gives you all the ways to take samples from any distribution. Yes, but we said when you do Bayesian inference, this phi of x is a posterior distribution that is represented with a computer code. How do you go and take samples from a distribution that does not fit in any of your standard distributions? So you need to know that, okay? Not that I will tell you in this course, right? So I'm going to tell you in this course things that they're already in the books, but you can extrapolate on your own problem on how you'll be able to take samples from any distribution, effectively pi of x. All right, so what I want to do is, I want first to tell you how to take samples from a discrete distribution. So if I give you a distribution like that, first I need your common sense evaluation of how to sample from a distribution like that, and then basically to formalize mathematically that's the correct way for sampling. So we have a discrete distribution here that takes three values, x1, x2, and x3 with these corresponding probabilities. How do we sample from this? Let me see if I have plots of this. Come on, where are my plots? Oh, there it is, okay? So, here is the how the distribution looks like. I don't know if it's the same as the one I had in the picture before, but basically a discrete distribution. And this is the CDF of the distribution. So how do you sample? I mean, you can of course read there, but looking at this picture of the CDF of the discrete distribution, how do you think potentially you can sample from a discrete distribution? I mean, obviously here you can see we have these delta functions jumping at every value of the discrete distribution, and eventually we go from 0 to 1. So what is a way to sample from this distribution? So obviously our samples would be 1, 2, 3, 4, or 5. And each of them has its own distinct probability. How do we sample from that? And let me put this equation in case it generates some ideas. Well, how about if I say the following thing, right? If you go and sample uniformly from 0 to 1, and we're going to assume here, right, that because that's the most trivial situation, that we know how to sample uniformly from 0 to 1. Okay? So if we can sample uniformly from 0 to 1, all right, how can we use the sample from a uniform distribution from 0 to 1 to actually compute samples of a discrete distribution? So you can go, let's say, and take your sample and here is your sample. What can you say about the corresponding sample of the distribution of interest? So I can sample uniformly from 0 to 1, but how do I find a sample for this discrete distribution? And actually, this is literally the proof that you need, right? If you use a uniform sample from 0 to 1, and this capital Pk are basically the summations from 1 to k of the probabilities corresponding to the value 1, value 2, the value 3, all right? I am saying here, if used between Pk minus 1 and Pk, all right, then this gives me, the probability of that gives me the probability of x being equal to k. Is that the case? Can you see that this is... So basically, if you sample U, and U is between, let's say, Pk minus 1 and Pk, according to this calculation, what do you take for x? You take 2. Can we prove this? I mean, actually, I don't know if there is a proof because the proof is, it's here, all right? Let me see if there is a proof. Here's the proof. Don't bother about this, right? Because basically, effectively, this is what we want to prove. Let's say we take the probability of u that we sample from a uniform distribution being between pk minus 1 and pk. So will you agree with me that this probability is equal to the integral of 1 du from pk minus 1 to pk? Where did the 1 du came? You remember is the uniform distribution from 0 to 1. So don't you think that this probability is this integral? Yeah? I mean, this integral looks actually exactly pk minus 1, right? Which is the corresponding probability for the uniform distribution. So the definitions of my pk is this, and the definition of pk minus 1 is that. So what I get is, I get that this is equal pk, which is actually the probability of x being equal to k. So by taking the samples of u, you actually sample from the exact discrete distribution that you are interested in. Okay? So in summary, basically, because you may need this, let me see what was my picture. What you do is, you take uniform sample from 0 to 1, all right? And you're going to hit one of these vertical lines, all right? So if you hit, let's say, from here to there, then your sample is x1. If you hit from here to there, it's x2, from there, x3, etc. Okay? That's the whole idea for discrete distributions. All right, how do we generalize this now to distributions that they are continuous? We generalize it using common sense, and the common sense is basically this picture. The same idea, exactly. And actually here it's even easier because you don't have any discontinuities or anything like that, okay? So this again, the CDF of the distribution from which I want to sample. Then I take, according to this picture, you take samples of u from 0 to 1 uniformly, and then what do? To find the corresponding sample of our, from the target distribution, what do we have to do? We know u, and we need to find y, so what do we need to do? We know u, and we need to find x or y, whatever, you know. Okay? What do we need to do? What is this process? We need to invert what? The CDF. That's it. Okay? The proof is actually trivial. Okay? Exactly the same way you can show if you do this calculation. Okay? And using the monotonic nature of the CDF, you basically get the correct, by sampling this way, you get the CDF of the target distribution. So the algorithm is basically you take a random number from 0 to 1 uniformly, you invert the CDF, and that basically gives you a sample from the target distribution. Do you see any problems generally with this sort of methodology of sampling? What do you need to have to make it of use? You need to have the CDF, okay? You need to have the CDF. All right? So this is for a Gaussian, no big deal. So let me show you a few examples, and I'm going to put all of them up so we can save some time. And these examples, by the way, they are not selected just as for demonstration purposes. They come up a lot in machine learning. So you may want to keep a note that you may have to come back to this type of calculations. So let's say if we want to take samples from the exponential distribution that looks like that. So the exponential distribution is from 0 to infinity, has a parameter lambda, and it looks lambda e to the minus lambda x. Okay? Obviously, this is an easy integral, so you can compute the CDF analytically. So the CDF, if x less than 0 is 0, greater than 0 is 1 minus e to the minus lambda x. So what we need to do is take a sample u from 0 to 1, and then invert the CDF. So basically, we have to solve for x given u, and my sample x is minus 1 over lambda log of 1 minus u. So effectively, what I'm claiming here is, if this is the uniform distribution, it generates samples from the exponential distribution as minus 1 over lambda log of 1 minus u. Okay? So if you need samples, again, from the exponential distribution, log 1 minus u, and the lambda is not very important there, log of 1 minus u gives you samples from the exponential distribution. And you can show, actually, even though it may look weird to your eyes, that if you take minus 1 over lambda log of u, that also gives you samples from the exponential distribution with parameter lambda. So both minus 1 over lambda log of 1 minus u and minus 1 over lambda log of u, they give you samples from the exponential of lambda. Okay? I want you to remember this, right? Uniform, log 1 minus u, log of u will do the job. And here is basically a histogram of the exponential distribution, starting by sampling uniformly from 0 to 1, and inverting effectively the CDF, and then putting all together, you get a nice exponential distribution. We don't need this. Another example. So we just proved this, right? Now, if you have a good statistics book, okay, that especially a mathematical statistics book, you will see lots of transformation methods that you never pay attention, certainly not as an engineer, but they're extremely important when it comes to sampling from complex distributions. So let me give you some of these formulas that you never think you will use. If you take IID samples from an exponential distribution with lambda equal to 1, and then you form a summation of 2 times the samples, or this summation, or this ratio, you can actually get samples from a chi-square distribution, from a gamma distribution, and from a beta distribution. So basically, according to these formulas, that obviously I'm not going to prove them because it's another course, another animal, but you can actually search on Wikipedia if you want on transformation. Well, you can actually go to gamma distribution saying samples of gamma distribution. I guarantee to you somewhere in that list, it will tell you take samples from exponential with lambda equal to 1, and then you form beta times summation of xi's, and that's a gamma, alpha, and beta distribution. The only limitation here is, for example, with this, what's the requirement on alpha? It has to be an integer. If alpha is not an integer, basically this formula is not valid. So you will need something else, something better, okay? So to apply these formulas, you need a sample from the exponential distribution. And how do you get samples from the exponential distribution? By sampling a uniform distribution. So you sample this, you sample that, and then you can generate anything basically you want to on this, okay? Here is another application of the samples of the exponential distribution by sampling a Gaussian distribution. And I believe this comes from Bishop's book. And I give you another proof actually on the following slide, a little bit different. So we want to sample from a Gaussian, right? We want to sample from a Gaussian. How do we sample from a Gaussian? Using this transformation basically rules, I'm going to give you another one where the samples are not from the exponential, but if you take 2 samples from the Gaussian with the standard Gaussian, so 2 IID samples, and you form a summation similar to what we had before, x1 squared and x2 squared, then it comes that this variable, x1 and x2 squared, comes from an exponential distribution with lambda equal to 1/2. So it's like sort of the reverse now, all right? So if you take two samples from the standard Gaussians, x1 squared and x2 squared is basically a sample from the exponential with parameter 1/2. So looking at this equation here, can you tell me how you can reverse this and tell me how you're going to sample from univariate Gaussians? Reverse this. So I said, you start with this, you start with that, then this is an exponential distribution. So if you want to take samples from a Gaussian now, what do? On a reverse. And actually, you're going to be getting both of these samples as IID in, so basically you build two Gaussians. Obviously here, if you look at the two equations, like r and theta will remind you polar coordinates. So what's the idea? Can we sample from the exponential of 1/2? And what do we need to sample from the exponential distribution? We need to sample from the uniform. Can we sample from this uniform from 0 to 2 pi? Yes. Well, if you take this on reverse and write x1 and x2 in terms of polar coordinates, r cosine theta, r times sine theta, then x1 and x2 will come to be Gaussians, standard Gaussians. Okay? There is another proof that I give you that does a little bit different type of calculation. There is a purpose to actually read this because you sort of it involves the transformation of variables when you calculate PDF, so you should look at that. So these are samples basically from 2D Gaussians, but I want to, before we finish, okay, if somebody asks you to take samples from a multivariate Gaussian, what do? Forget 1D, forget 2D. I didn't tell you that 2D was in the previous slides. If somebody tells you, remember in your homework you had a 50-dimensional Gaussian. Did you have, actually you did have to take samples from the Gaussian, right? How did you take those samples? Did you cheat? You say, MATLAB, give me samples, right, in 50 dimensions, that's what you did? Come on, guys. Remove points, all right? So how do you think MATLAB does it? But 50 dimensions eigenvalue will be very complicated. You know, these eigenvalue problems are very nasty. Do you really need to solve an eigenvalue problem? So basically what you have to do is you have to do Cholesky decomposition of sigma, all right? And you don't need to compute eigenvalues for that. So you do a Cholesky decomposition, and then I claim, all right, that if you take the sample Z as IID samples from the Gaussian standard distribution, mean 0, standard deviation 1, effectively you can generate samples from this multivariate Gaussian by adding the mean plus S times this IID samples Z. You may say, how is that working? Well, of course, you know, the Z's have 0 mean, so obviously the mean of X is mu, that's nice. And let's look at the variance. So the covariance, basically, if you compute the expectation of X minus mu, X minus mu, X minus mu is S times Z, X minus mu transpose is Z transpose S transpose. This is out. This is the covariance of this IID sample, so it's identity, so it's SS transpose, which is sigma. All right, so you can take samples from a multivariate Gaussian without having to rely on MATLAB, using basically a Cholesky decomposition of sigma. So what are we going to, so we're going to continue, of course, on this topic on Wednesday. The slides are basically, you know, I put the slides basically for the whole week, more or less, so you can read them. But we're going to discuss this accept, reject methods for computing samples. And those methods will be extremely important when we do Markov chain Monte Carlo type of methods, okay? Again, we don't have a lot of time about Monte Carlo methods, right? So I'm giving you this because there is limited information in the books. You need to know this knowledge, but it's really, you will never take a machine learning course where any professor will spend more than 10 minutes on this, okay? They assume you know it, you know, et cetera, et cetera. We used to teach literally a course on its own on this topic a few years back, but right now we only have time for maybe four lectures or so, including dynamical aspects of this. So office hours today, and I will see